First of all, I want to introduce the concept of a type curve. And this is where we bring the equations together. Okay? So we're going to start by blending transient and boundary dominated flow together. And I can tell you that any piece of software that's out there that's doing analytical modeling is going to be doing it this way. It's always done the same way. Okay? So when we have transient production, we're going to use a transient equation. When it goes into boundary dominated flow, we're going to use the boundary dominated flow equation. The analogy I like to use here is that of someone or people running a relay race. The person who's running the relay race, who has the baton, runs through, and then someone runs along beside them and the baton is passed over. That's what's happening with these curves. Okay? This is the transient curve is the one with the baton. He passes the baton over to the boundary dominated curve, and the boundary dominated curve takes over. In the place where they're both the same, that's the transition place, and it has to be smooth through there. In the same reason that a relay race has to be smooth through the transition period. In other words, when I look at the overall equation at the end, I shouldn't be able to tell by looking at it that it actually changed. You know, that it's a piecewise or segmented equation. There's two separate things that were brought together, but they look like they're seamless. And that's what we do here. Okay? So we start with a transient equation. The key thing is how do we know when to switch from the transient equation to the boundary dominated flow equation? How would we know that? Well, we can use what's called time to pseudo-steady state. And time to pseudo-steady state is nothing more than the radius of investigation, but solved with time. Okay? So picture in your mind what we want to do here. We've got an area in mind. So I've got a reservoir that I know has one section. I'm going to have that as my input. It's 640 acres. I know the permeability is equal to 1 millidarcy. And what I want is the equation as for production as a function of time for a well flowing at a constant pressure of 100 psi. Okay? So give me the equation that does that. Well, that's a function of two separate equations. It's going to start with the transient equation. As the pressure transients move out, I'll have and I'll use a different color to show this. So I'll have a transient equation at the beginning, which is going to do something like this. And then at some point in time, when these pressure transients reach the boundary, remember I throw the rock in the pond, the pressure transients reach the boundary, it's going to switch over to a boundary dominated flow equation. And if it's constant pressure, then that boundary dominated flow equation will be the exponential equation. Right? So this one's going to be transient, this one's going to be boundary dominated flow. There's going to be a place where they transition. And to calculate that place where they transition, I simply use the radius of investigation calculation. So for radius of investigation, I put in, or area of investigation, I put in my 640 acres. And what I do is I calculate the time. I know the permeability, I know the phi mu c, and I'm going to calculate the time that it takes to reach that fixed region of investigation that I've input into here. And that's called the time to pseudo-steady state. Okay? So time to pseudo-steady state is equal to the time it takes for pressure transient, time it takes pressure transient to reach a predetermined region of investigation. Okay? So I've already decided what that region of investigation is, and I want to figure out how long it's going to take to get there. So once I know that time, then I can calculate exactly where that transition point occurs. So now I have my full equation. So that's pretty powerful. Now I've got a Q of t that consists of transient from 0 to time pseudo-steady state, switches over to depletion from time pseudo-steady state and higher. It's one single curve that can represent production starting from 1 millisecond after I open the wellhead valve all the way to time infinity, because it covers the whole gamut. It covers the early time, transient flow, all the way into the late time. All of the models and type curves and forecasts and everything in our software and anybody else's software that's doing analytical modeling of production data is doing it this way. This is the method that is always used to generate these forecasts and history matches. All right, now we're going to switch gears on you a little bit. Okay, now that we have an equation that works and we like it and it looks good and everything's happy, we're going to change the rules a little bit, because effectively what we've done up until now is we've worked the problem from in the forward direction, which is the way most people think, right? I've got some parameters, permeability, skin, drainage area, so on. I'm going to take that information and generate a production response to go with that. That's sort of the modeling or reservoir simulation mentality, right? It's a forward modeling problem. Whenever we do analysis and interpretation, we're turning that upside down. We're doing the reverse of that. Because what you're actually going to do is you don't know what the permeability and skin and drainage area are, but you already have the data. So what you want to do is actually use the data and try and extract that information. So it's the reverse problem, right? So a little diagram that I like to use, which I think illustrates this very nicely, is we start with data, and we end up with parameters or results, whatever you want to call it. And these may be perm, skin, drainage area, etc. This is forward. I'm sorry. I did this the wrong way. This should go back this way. Okay. Let me try this again. We start out with parameters. K, skin, drainage area, etc. Okay. And we're going to go forward. And we're going to generate data. Now when I say generate data, effectively we're generating that Q as a function of time. That data might be QT for constant pressure, or it might be pressure T for constant rate. Those are really the only two data sets that we can generate, okay, at the moment. In a few minutes we'll show you how you can generate lots of other different types of data sets for different operating conditions. For example, when the rates and pressures change together. But right now, mathematically, we can do QT for constant pressure, or pressure curve for constant rate. And we've shown how we can blend together the transient and boundary dominated flow analyses. So we've got a very nice little system there. When we're doing production data analysis, we're doing the reverse of this. In other words, we start out with the data, right? We don't know what these numbers are. So we start out with the data, and we need to get back to the parameters. So this is the forward problem, and this is what we call modeling. Analytical modeling, or even numerical modeling. When we do simulation, we're doing the same thing. Okay, it's forward modeling. Whenever we do analysis or interpretation, or whatever you want to call it, it's the reverse. So it's always a reverse problem. Okay? And as you might suspect, solving reverse problems is a lot more difficult than solving forward problems. Forward problems are usually well defined, and the errors don't have as much of an impact. Solving reverse problems are notoriously difficult. They're subject to very small errors. They're unstable. They're unstable problems to solve. Okay? For instance, if I throw a whole bunch of error into this data, and solving this becomes a big problem, right? I may not be able to get a unique answer for this out of it. Going this way, I always get a unique result. Going this way, I may get 5 or 6 different answers that all fit that data. So this problem is this is the more valuable problem for us to solve. This problem has a lot more value for us to solve, because this is the problem that takes data which is known and turns it into some usable parameters which are unknown. Okay, now having said that, that's where type curve analysis comes in. So that's what we're going to use type curves for. Okay, type curves assumes we already know the data. We don't know what the parameters are. So the first thing I'm going to do with type curves is I'm going to plot them on a log-log plot. And this adds a new visual dynamic, as I'm sure you would agree. When you look at this plot, it looks significantly different from this one. But they're actually the same data. Okay? But this adds much more dynamic sort of appearance. And one thing that you'll get immediately from this that you don't get from this is that spot in the middle there where it transitions. This is the time to pseudo-steady state. So this is where we transition from transient flow to boundary-dominated flow. There's an inflection in the data where that occurs when you plot it on log-log coordinates that you don't see on just the linear plot of rate versus time. So this transition here is a transition from upward concavity to downward concavity. And we can see very clearly in the type curve, or in the production curve, the Q of T, this guy right here, where that occurs. Now I've plotted two separate curves on here. One of them is red and one's blue. The red one corresponds to the constant pressure, the analytical constant pressure solution. The blue curve corresponds to the constant rate solution. Okay? So everything past the dotted line, that's boundary dominated flow. Constant pressure is exponential. Constant rate is harmonic. One thing you'll notice about harmonic is that it has a unit slope. Okay? It's a straight line, and it actually goes down 1 log cycle for every 1 log cycle it goes across. So it's a unit slope. The red curve curves down, and that's exponential. So these two diverge significantly as time goes on. One thing I didn't talk about is the difference between constant rate and constant pressure during the transient part of the solution. I only generated one transient equation for you to see. The one that I generated and showed you was constant rate production. Well, it turns out that constant rate and constant pressure, theoretically, really don't have all that much difference. They almost have exactly the same looking production response. So that's useful because that means, we don't really care. We don't need separate equations for constant rate and constant pressure. They're almost the same thing. Okay? So we can take a really nice approximation here and just say, hey, I'm going to use the constant rate solution, and it'll represent everything that's in the transient side, provided that I use the normalized rate as my plotting variable. Right? If I didn't use the normalized rate, then it wouldn't work. Because if I plotted just rate, and rate was constant and pressure was changing, then I wouldn't get anything. So I have to plot the normalized rate here, and everything will work here with one single curve, but I obviously can't do that on this side. When I'm on the boundary dominated side, they diverge pretty significantly. So the key thing with the log-log plot is visually the shape of the data. We have concave upwards in the transient part, or infinite acting part. We have concave downwards in the boundary dominated flow part. Okay, so what exactly is the type curve? Well, what I just showed you here is a type curve, but what makes it a type curve? Well, one thing that makes it a type curve that we saw right away is we plotted on a log-log plot. Okay, well that's sort of trivial. I mean, I can take anything and plot it on logarithmic coordinates. That's not what makes it a type curve. What makes it a type curve is I make the model itself dimensionless. So I'm going to take the data that I generated that made that production response, and I'm going to make it dimensionless. And dimensionless for the reservoir well system that I'm dealing with. I'm going to talk about how and why we do that in a minute. Another thing we do with the type curve is we have to assume constant operating conditions. Okay, that's just the math. We have to do that. So you'll notice here we have either constant pressure or constant rate. We have to assume one or the other. The type curve, as we mentioned before, is a valuable tool for interpretation of production and pressure data. So what are we going to use the type curve for? We're going to use it to get from here back to here. Okay? So the data we have, we're collecting it, we're measuring it. The data is cheap, right? We got the data, it's inexpensive. We're collecting data points every single day. It's easy to get our hands on this. What's hard to do is to come up with some kind of analysis that's going to allow us to extract information about the reservoir. Okay, what I want to do here is give you an example that will illustrate why we use dimensionless numbers, dimensionless parameters, and how we use dimensionless parameters. Okay, so how do we define dimensionless parameters? And Fetkovich many years ago did this very nicely and cleverly when he created his type curves. So what he did is the equations that he had access to at that time were the ARPS decline equations. And he said, I'm going to take all these equations and make them dimensionless so I can turn them into type curves. And they're really the simplest equations to use to turn into type curves. So we're going to use these to illustrate the concept. All right, so what you're looking at here are a series of curves. They're plotted on the log-log coordinates. And these curves are nothing more than just the exponential, which is shown in red, and all the different hyperbolic decline curves with different b values. And then finally, the dark blue one at the end there is the harmonic. So that's where the b value is equal to 1. And you'll notice that Fetkovich didn't go any further than that. Right? He didn't generate anything past there. And there's reasons for that. For each one of these equations, or for each one of these curves, there's a dimensionless variable and a dimensionless equation. So what Fetkovich did is he defined this QDD. The big D stands for dimensionless. Little d stands for decline. And he defined it as being Q, in other words, production rate is a function of time divided by initial production rate. This is a normalized production rate, not the same as Q over delta P, but it's Q over QI. So if you think about this, it makes sense that these are all going to start at 1, right? It doesn't matter what your production rate is. If you normalize it by the initial production rate, it's always going to start at 1. So these curves all become asymptotic to 1. On a log-log plot, they're never going to reach 1 because you can't plot zeros. So there's no time equals 0 on here. So these will just keep going back, back and back and back in time. TDD is dimensionless time. This one is defined as the decline rate multiplied by time. Okay? And this is going to be dimensionless as well. If you think about it, decline rate is in percentage decline per year. Time is going to be measured in years. That will cancel out and you get a dimensionless number there. So to illustrate how this works, what I'm going to do is I'm going to use the exponential equation to show this. And it's actually a clever little thing that removes the dimensions from the equation. So we start with Q. This is the dimensional exponential equation. E to the negative d I t. Okay? So this is exponential, but it's dimensional exponential. And then we've made these definitions. We've said that QDD is equal to Q over QI. And we've said TDD, here, let's put TDD over here. TDD is equal to DI times T. Okay, so what I want to do is make these substitutions in here. So Q is equal to QDD times QI based on this. Okay? And T is equal to TDD divided by DI based on this. Okay, so now I'm going to make these substitutions into here. Okay, so Q, as we said, is QDD, so we get QDD times QI equals QI, and E to the negative DI, T is TDD divided by DI, so TDD divided by DI. So you can see what Fetkovich has done here. He's he's come up with these definitions of dimensionless variables such that the QIs cancel out and the DIs cancel out. Okay? So there's a QI on both sides here. They're going to cancel out. And there's a DI on the top and the bottom of the exponent, and they're both going to cancel out. So what you're left with is QDD equals E to the negative TDD. So what's the significance of that? Well, the significance is that exponential equations are great, but they're all over the place, right? You could have an exponential equation that starts at 10,000 barrels per day and declines at 10% per year, or one that starts off at a barrel per day and declines at 1% per year. They're two totally different equations. And effectively what I've done here, or what Fetkovich has done, is he's removed the dimensional component of it and he's made it generic. And what that means is that instead of needing a different exponential curve for every single set of initial rates and decline rates, of which there's infinite number, all I need is one. And I match every single production data set I have to that one equation. Okay, so the type curve, the purpose of type curves is that the whole world fits on it, so to speak. Right? If you have a well that has exponential decline properties, it doesn't matter if it's shallow gas, southern Alberta somewhere, or if it's in the North Sea. Okay, those will be drastically different production looking situations. But they will both, if they have exponential properties, they will both fit on that curve. And that's the purpose of doing a type curve. The part of it that we can't remove is the b-value, because the b-value changes the shape of the type curve. So the b-value, we need a separate type curve for all of these ones with different b-values. So the convention is to generate discrete solutions for different chosen b-values. The drawback of a type curve or a set of type curves is I don't get a single curve for every single b-value. For example, I don't get one for a b of 0.441. I might get one for 0.4 and one for 0.5. So there's only discrete solutions. But if I can take and match my data to one of those curves, then I've got an answer that's good. Okay? So I can apply this concept of dimensionless definitions, variables, to all of the type curves. All right, here's an illustration of what we're talking about. If we started with raw data, I made the reference earlier to southern Alberta well with low production rate and low decline rate, or a North Sea well with a high production rate and a high decline rate. These are the two examples. They're both exponential, but they have very different looking production profiles in terms of their raw data. When I convert their data into dimensionless variables and plot them on the log-log plot, they both superpose, or they both overlay each other exactly. Okay? So they both fit onto the same type curve. And you can imagine there'd be an exponential type curve matched right to that data. So that's the value of doing the using type curves with dimensionless variables. One thing to notice on here is even though these two production data sets start and end at exactly the same time, in real time, in terms of dimensionless time, they start and end at different places. And the reason is because well number 2 has a much more of a percentage decline over its time or over its life than well number 1 does. So well number 2 goes further in dimensionless decline time than well number 1 does, because it's got a higher decline rate. And remember, TDD is equal to decline rate multiplied by time. Okay? So this sort of illustrates why we want to do this. Now when we actually do the type curve matching, we're kind of doing the reverse of that. Okay? What we're doing is we're taking the data and we're going to match the data to the type curves underneath. I'm going to show you this live on the software so you can get a sense for what this looks like. Here's my Fetkovich. I'm going to turn that one off. There's my data. I'm going to move my data around, and I'm going to find the match position and match it on the data set. Now if we zoom in and take a look at this, the type curve that's been chosen here as being the one that fits the data the best is a B value of 3. So there's a couple things going on. One is that I've chosen the location of that data that best fits, and I've also chosen the curve from a family of different curves that it fits on. And that's basically, in a nutshell, that's type curve matching. So the process is actually very simple, right? It takes an engineer with a certain amount of judgment to do this properly. In some cases, it'll be easier than other cases. And it really depends on the quality of the data. If the data has very good quality, it'll usually be very easy to do this, and we'll get fairly robust answers. If the data has poor quality or has a lot of scatter in it, then it may be much more difficult. Okay, so we talked about type curve matching and how you can use the type curves to extract parameters from the data. And really, that's an example of the reverse modeling process, which is what analysis is. What I want to do now is extend that concept, because what we showed was a very simple application of it using ARP's decline curves. The fact is we can create type curves from any reservoir model. And we've already investigated some more sophisticated reservoir models based on analytical equations. So we've generated those analytical equations already, and what I'd like to do now is turn those into type curves. And in fact, luckily we don't need to do that from scratch. Fetkovich has already done that, and he did that years ago, and created a set of analytical type curve models as well. So these have tremendous amount of value, particularly in the transient part, and can be used to evaluate production data, permeability, and skin. So what I want to do is talk a little bit about these curves and get an understanding for what sort of parameters we can get from them. Fetkovich uses his dimensionless rate and dimensionless time coordinates. And what you're looking at on the screen right here is excuse me, a set of analytical model type curves. And these are all created at constant pressure. Okay, the color coding here shows us which shape or which reservoir geometry goes with which type curves. So we have the red reservoir corresponding to the red type curve, the green to the green, and the blue to the blue. What the different shapes in here represent, if you'll notice, is that they all sort of have similar outer circle radiuses, but they have different inner circle radiuses. So the inner circle is the well radius, and that's what we're really interested in because it's a transient problem that we're solving. So it's near the wellbore that we're interested in. So if we take a look at these things, and in your mind you can see where the transition point where they go into boundary dominated flow. This is constant pressure, so everything is going to become exponential. And since they all have the same external radius, they're all going to go and become exponential at the same point in time, and they're going to merge together at that point in time. Now, Fekovich has scaled the type curves so that they do that automatically. Okay, so the scaling factor has created this blending of type curves at the exponential. During the transient, you can see there's a somewhat of a fanning out of type curves. There's a whole series of different type curves for different transients that may be occurring. Why is there a whole bunch of different models here? Well, the answer is the wellbore radius for each of these models is different. Okay, what does it mean when I change the wellbore radius? What it really means is if I have a small wellbore radius, that's a lot like saying I've got a well that's got some damaged skin. If I've got a large wellbore radius, that's a lot like saying that I've got a well that's stimulated. Okay, it's got a negative skin. So we're using the wellbore radius concept as a proxy for skin. And that works very well. That's a very effective way to do type curves. Okay, so there's this concept of skin and it's built into the type curve. So this number, this RE over RWA that we're seeing here as 10, 100, and 10,000 represents the ratio of the outer to the inner radius. So we've got this circle, two circles really, where we've got an apparent wellbore radius on the inside and an exterior radius on the outside. And we're looking at this RED, which is dimensionless reservoir radius, as a ratio of RE to RWA. Okay? If this number is very, very large, that suggests that the RWA is small for a fixed outer volume. If this number is very small, then that suggests that the wellbore radius is larger. And so there's a direct correlation to this number, how big this number is, and the state of skin, so to speak, whether it's a damaged well or a stimulated well. So the red curves up here are going to be stimulated wells, and as we start to go down towards the blue curves, we're going to become more damaged. That's kind of nice because there's a visual way now. In fact, I don't even really need the numbers. Just as a visual way, looking at the colors on the type curve suggests that those ones that are closer to the reds, in other words, they have a sort of a steeper decline at the beginning, are going to represent stimulated wells, wells with a negative skin. For example, tight gas wells that are fractured are usually going to be up here. Okay? As opposed to damaged wells, which are going to have a flatter sort of production performance at the beginning. So there's a definitive sort of shape that's going to tell us a little something about the transient state of the well. Is it a damaged well or a stimulated well? That now we have, in addition to the diagnostic where we get an inflection between concave upwards and concave downwards. So now we really have two indicators on the type curve that we can look for. One is whether it's a transient, stimulated, or damaged well. And the other one is simply the transition from transient to boundary dominated flow. And we can see that in the shape of the data. So that's quite a good diagnostic to have. These are the definitions that Fekovich uses, and we don't need to go into the details on them, but we do want to show that the RED is built into those definitions. So that's important. They're scaled in such a way that RED, dimensionless reservoir radius, is built in. We can use the QDD and the TDD together to solve for things like permeability, dimensionless reservoir radius, which in turn gives us skin. There's an equation that can tell us what the skin value is based on knowing what the reservoir radius is. Okay? Because we have what's called a real reservoir radius RW and an apparent reservoir radius RWA. If we know both of those, we can calculate the skin. And then finally, we have RE, and that can tell us the drainage area of the reservoir. So we can use the Fekovich type curves for three different things. We can use them for establishing permeability in skin. Sorry, that's two of those things. And then the third thing is we can use them to establish the reservoir radius, or drainage area. And the type curve matching procedure is very similar for the analytical models. We have the data sitting up here. We can move it around and match to the type curves in exactly the same way that we were doing with the boundary dominated flow or the ARPS depletion part. The difference is you're matching on a different part of the type curves. So I want to show how this all sort of ties together. We started in looking at Fektovich really focused on the right-hand side of the plot. The right-hand side of the plot is where the ARPS depletion stems occur. And now what we've looked at is the left-hand side of the plot. This is where the analytical transient stems occur. And Fektovich was very clever. He was able to blend all of these together in one sort of seamless type curve analysis. And so I want to show two examples. The first one is boundary-dominated flow, where we're really focused on matching this part of the data. And the reason we're doing that is because we can see there's downward concavity in the data. Okay? Then the downward concavity in the data matches a specific shape of one of those boundary-dominated curves. Let's look at another example. In the other example, we've got transient production. So we're going to be interested in identifying the shapes that are consistent with transient production. And we probably want to filter some of this data away because it's noise. But we're really interested in that underlying reservoir signal. And there it is. So we can see we've got some very slight upward concavity. We don't have the transition into boundary-dominated flow yet. So we're really not matching anything down here yet. And if you've got transient data, this is the sort of signature that you're going to see in your data. You simply won't have production that fits on these curves down here. So therefore, you know that you're not into boundary-dominated flow yet. This is still transient data. So I'm going to match based on one of those transient curves and then extract the particular reservoir properties that are appropriate. Okay? Remember, in transient production, what's appropriate is permeability and skin. In boundary-dominated flow, what's appropriate is reserves, reservoir volume, things like that. So you're not always going to be able to get all the numbers out of this. In fact, RTA will tell me a reservoir volume that goes with this, but it's non-unique because I haven't seen the boundaries yet. So the only one that really makes sense is going to be the one that represents the minimum or the contacted reservoir volume. And that can be determined by moving this as far to the right as I possibly can, because I haven't seen all the boundaries yet.